Hello and welcome back to the Hyperthesis. We are now at the episode 35 and today we're going to talk about more casual topics today. My name is Pheely.
I'm Patrick.
And I'm Liam.
All right. So today we're a little more spontaneous. Let's do things a little more abruptly. So any intro topic that is interesting today?
Yeah, I have a really interesting topic from a talk I attended last Friday. So this talk was given by a professor in my department at the University of Alberta, who's Dr. Paul Myers. But him and his research group focuses on the North Atlantic and Arctic Ocean and doing models for the different circulation and different flows that happen there. And that area is particularly important because we see a lot of outflow from the Arctic Ocean into the Atlantic Ocean. And you also have giant masses of ice there, such as the polar ice, I guess the sea ice cap, along with the entire Greenland and Canadian islands up there, all covered in ice. So it's a really complex and interesting area to model. And their models are very intensive. They try and predict, I think, 50 years into the future under different climate conditions. And yeah, it's pretty intense stuff. But one of the main takeaways from that talk was that if you've taken an earth science course at all, just introduction to earth science, or even learning about it in science in high school or in grade school, you may remember seeing a map of the world, and in the oceans it has these currents. So these hot currents that go on the surface of the ocean going from the equator and up northwards or southwards, where there's a lot of water carried on them, and then they're cooled because they're further north, close to a lot of glaciers and ice, and that sinks to the bottom and then is carried back to the equator. And these giant convection currents essentially are shown to circulate water throughout the world. So on the example that was in the talk and that I've seen in textbooks before is water that's going up north to the North Atlantic, then down and around the southern tip of Africa and into the Indian Ocean, and then circulating there and with the Pacific, and then going back. But a lot of these convection currents are actually false. So with the currents that are around the tip of South Africa, instead of like a steady current like you might expect, or like what you might have seen in a movie like Finding Nemo is the one that pops into mind, where they're riding the current. Instead, there's a lot of backflow from the Indian Ocean into the Atlantic Ocean due to vortices. So there's no like steady stream. It's just a lot of vortices that are formed from water shoving up against essentially the south of Africa and forming these turbulences. So this group specifically looks at kind of the area between Greenland and Canada. So lots of ice there. And that's the main part where water flows from the Arctic Ocean to the Atlantic Ocean. And that follows the flow from the Pacific up into the Arctic, kind of pooling in the Arctic and going around the north of Canada, and then down through between Greenland and Canada. So there's a lot of very cold water going into the Atlantic, and a lot of complex circulations are going on. And we think of that again as a steady stream, but it's definitely not the case.
Well, I think the magnitude of like this type of earth science research is such a different, it's so different from physics, right? Where it's like, oh, well, you have like this many variables that happen that like part of your system. You try to predict 50 years, and you think about physics. I imagine what Liam is doing. The system's like really tiny, like with quite a few variables, but let's predict what happens in the next microsecond, or a second is a long time. And now you're doing to me it's like approximation, which is extremely rough, like compared to like a very precise like physical description that we are more familiar with in physics. It's just fascinating how people actually can like make these model work even. Like we are struggling to solve like a convection equation in 2D, and now you're like, hey, you know what? Let's predict where the currents are in the world.
Yeah, these ultra cold atom systems that I study are very, very, very nice in the sense that they're so cold that you don't have to worry about like thermal fluctuations or thermal phonons or any of this weird stuff that you get in kind of regular fluid mechanics. And yeah, it's just that's why the weather's so hard to predict, is you can't really accurately describe it, and then you have chaos to deal with, and there's just like a million things. So another thing I find interesting is that, well, you have all these like currents and stuff in the ocean and water, and I think depending on what layer of the ocean, like as you go deeper, you get kind of these different types of water, and you get currents in them which are separate from one another, and then you have atmospheric currents, like you have like the jet stream over North America, and it's all fluid mechanics. I find that stuff really interesting. I wasn't really interested in it as an undergrad, but the older I get, the more I'm interested in it.
Yeah, no, it's super cool stuff. And that was another thing that was discussed in the talk was the fact that when you have sea ice over top of the ocean, not a lot goes on because it's so insulating. So you might have like very cold air, but this layer of sea ice is so well insulating that the water beneath is still like a nice 4 degrees or 3 degrees Celsius. Whereas when you don't have this sea ice present, when the sun hits that, it warms a bit of the water, but it essentially starts these very, very deep convection currents that kind of interplay between the salt water and fresh water that's present. So you have these massive vertical convection currents that are going many kilometers deep and coming up again. And these are something that is essentially as the I'm trying to remember the exact mechanism, but when you don't have that layer of ice, the water cools, and so then it starts to sink, and that brings up hotter water, which then essentially emits more and then cools and then has these very large convection currents. But yeah, these are chaotic systems, as you said, with a lot of variables. So some will look at the atmosphere and the water, whereas others will just look at the water. And of course, there are atmospheric models as well. But just to give you an idea, so to solve these, it's not analytical, it's all numerically solving PDEs. And there are, they've broken up this area into like 0.1 by 0.1 degrees in terms of latitude and longitude. And that's quite high resolution. And to compute this all, it's tens of PDEs for each little square in the grid. And I think each one takes 40 seconds. Now, I forget the time scale, but I think it might have been on the scale of hours or days. So when you're trying to model 50 years into the future, if it's taking 40 seconds to just solve one little grid, like a grid of a couple thousand by a couple thousand, it's an insane amount of computation time.
There's also time scales to worry about, and I completely forget how this works. But when I studied a little bit of fluid mechanics, you can basically find that the reason, like, yeah, you can predict kind of overall weather trends over long periods of time because somehow the equations that you find they work over those time scales, but on short time scales, everything breaks down because chaos and whatnot. So when you're predicting the weather, you have to choose these different time scales, and I think we talked about this before. Like they're consistently, when you're trying to predict the weather, they're plugging in new parameters all the time to update it so that the chaos doesn't take as much of an effect over time. It's pretty wild stuff. Oh, some other completely unrelated. But did you know that you can have quantized vortices? I didn't know that until recently.
So it's either a vortex doesn't exist or like there is a vortex or there
It
isn't
has
one?
like discrete values of angular momentum. So vortices are the huge thing in these ultra cold atomic gases. But they're kind of like quantum vortices. Although I that's kind of all I know about them. I need to read up more on it. It was a chapter that wasn't included in my comprehensive studying, so I didn't bother read it.
Yeah, it sounds like a made up thing. Like, come on.
No, it's not made
Discrete.
up. You can measure it. It's experimentally verified.
What do you mean discrete vortex? How do you be a vortex if it's discrete?
Well, it has discrete values of angular momenta.
What's a medium for the vortex?
Like a Bose-Einstein condensate or some superfluid or ultra cold gas. You get vortices and all these things, but it's like in quantum mechanics, particles can only have discrete energies. Well, they can also only have discrete angular momenta. It's the same thing with these vortices and kind of a many body ultra cold gas.
I guess so. If you can only have discrete momentum, then
Yeah,
you're gonna have discrete. It's just a weird way to say discrete vortex. It's just like a matter of coordinate system, right? Like it's gonna be just still discrete momentum. It's just that's
yeah.
it.
I need to read up more on it, but that's kind of the way they refer to them for whatever reason.
Oh, because it sounds cool.
Yeah. Oh, and so this is something I learned about recently, which is also it's kind of related to like earth sciences. So seismic waves, like things that cause earthquakes. I don't really know much about it, but I know. Have you guys heard of metamaterials before?
Oh, I heard of metamagnets. But
It's a metamagnet.
what is a metamaterial?
Metamaterials are basically materials with negative refractive index. So they don't
Hello?
yes.
You're saying it's going to a material and it go faster to speed up light?
No, it's still less than 1. It's just negative. It's it's greater than
all right.
-1. So there are these materials you can make and they don't occur naturally at all, but you can combine different like molecules and elements and rearrange them in lattices a certain way so that so with like a regular refractive index, if you have light going from air to water, it changes its angle, and you can get that
Yeah.
effect where you have like say you have a pencil and a cup of water and it looks like the pencil's been cut in two because what you see from the side in the water is shifted from where the pencil actually is, right?
So is it just like total reflection?
It's like combining refraction and reflection. So as the light enters the water, it'll actually kind of turn around, but it'll refract, but it will do it and go the opposite direction.
Well, I think that's just called reflection.
No, reflection is when it's related to reflection, but
Yeah, it doesn't look like the angle is the same because with like perfect reflection, you have
yeah,
it coming in an angle, it leaves an angle. But when it crosses the boundary between the new materials, it goes in an angle and then reflects. So it kind of goes back in the same direction, but at less of an angle.
yeah. It's like if the light enters, it's still going like imagine it's entering a cup. It's still going down the cup, but it kind of like changes its trajectory, so it's not going in kind of a straight path.
I feel like people are just confused their like nomenclature. Just don't know how to define things. You know what? Let's just define a new word to describe what are the combination of reflection and refraction. So it's like
Yeah,
so normal reflection, you're gonna have the incident angle and the outgoing angles be the same, right? That's like the by definition. So you're saying this time that reflection, quote unquote, doesn't have the same angle going out. Does it break any kind of law?
oh, you can do it. It's I mean, there's a ton of people study this who are a lot smarter than I am. So yeah, there's a picture of it. That's the idea. You see how the straw? It's kind of like it's still been kind of reflected, so it changes its direction in the water. For people listening, you can just Google metamaterials or negative refractive index. Anyway,
It
yeah,
goes the
yeah.
other way, right?
But the
Yeah.
I
Why?
don't know. It has to do with kind of this. I've only learned of this like 3 days ago. I'm not an expert, but there's the point is that you can do some weird things with these metamaterials with these negative refractive indices. You can go past the diffraction limit, which is something we talked about last episode with Cat. The fact that microscopes can only work so well because the wavelengths. So if you try and look at an atom, say the wavelengths of visible light are larger than that atom, so you can't actually see that atom using a visible light microscope. And it has to do with the fact that for like a microscope, the light that leaves the lens, there's what they call far field radiation and near field radiation. So the far field radiation is the stuff that comes out of the lens and goes into your eye when you're looking through a microscope and you say, okay, I see a cell or something through my microscope. But this near field radiation is these evanescent decaying waves. And that contains information on the kind of like the zoomed in pictures of, say, whatever you're looking at, but it decays, so it never reaches your eye. But somehow these negative refractive index materials, or these metamaterials, they can somehow, this reflecting part of them allows them to focus these evanescent waves better, so you can actually go past the diffraction limit somehow. I don't really understand it, but they've done it in some senses. And the point that I was getting to is that you can do it for more than just light. You can do it for sound waves, metamaterials. You can do it for these seismic waves, and they haven't implemented anything yet or experimentally tested it, but they have these like systems that they can put underneath like buildings or like a nuclear reactor or something, and it basically, you can create like invisibility cloaks with these metamaterials. So they can put these structures underneath a nuclear power plant, and the waves of a earthquake can be kind of like these negative refractive indexes can kind of make the waves go around the structure so it's not damaged. And you can do it with light. You can create like cloaking devices with light. It's kind of neat.
Well, it looks like what happened is like when the ray hit the surface, instead of the surface being, in the direction of not like the normal, the conventional direction, because I was going to use the word normal. The actual plane of the incident is actually perpendicular to or normal to the surface. So instead of thinking of refraction, it's almost like a reflection to the plane that perpendicular to that to the surface. I think that's how negative refractive can be thought of. I think it's like it's reflecting to the plane 90 degrees to the surface.
That's a good way to put it.
Just a thought and a question I have with this is, what are the conditions for total internal reflection? Because we know that for total internal reflection, say of like a glass prism, it needs to be going at a certain angle so that it bounces off and then it does internally reflect. Whereas in this case, I'm just curious what the conditions would have to be to totally internally reflect, which also produces some evanescent waves.
Well, we know about the Brewster angle that create that total internal reflection, right? I think that's what it's called, unless I got that wrong.
I feel like I've heard that, but it's been so long. It was like this ancient memory in my brain. When you said it, I was like, oh wow, I haven't heard that in a while.
Well, maybe the metamaterial has some like I don't know, the internal arrangement such that like the plane of reflection is not like normal.
The reason why it does it is it's to do with like, I mean, water. You can't have a negative refractive index of water. That's just kind of like a toy picture to look at because it's easy to imagine the straw in your water being reflected. In reality, these materials, I think they're like more of these fancy types of metal or glass or something. They're these like lattices that you can kind of mesh together, or even like plastics and polymers. Somehow you can kind of mesh them together in such a way that you get this weird behavior. I don't know the details, but that's what I read a little bit about. Yeah, and I think they're kind of neat, especially for like preventing certain structures from being heavily damaged by earthquakes. And you can even create like you can use them for sound waves as well. Although with sound waves, like again, for optical waves or sound waves or seismic waves, the structures you're putting together to create these metamaterials are very different, but they're kind of described by the same underlying math, I think. Anyway, I thought that was kind of neat, so I figured I'd bring it up.
Yeah, because the seismic wave, you have like P wave, right? And you have the other wave.
You also have S waves, which are not S waves. Confusingly enough.
Yeah, P wave is pressure wave, basically.
I know in like quantum mechanics, you get S wave scattering and P wave scattering and that stuff too, but I think they're different. I think it's just like bad terminology.
To be fair, there are only 26 letters in the alphabet.
Yeah, there's our friend Dean in laser physics. There's this thing called Stokes phenomenon. But also in the field of, like, in the mathematics stuff I study, there's something called Stokes phenomenon as well, but they're completely different things. They just have the same name, right? It's like the same with like Euler and Cauchy, these famous mathematicians. They have like a million things named after them, but
Yeah, they're doing too much, man. Like Penrose, like Roger Penrose. He has a bunch of stuff with tensor, had stuff
yeah,
in math.
there's two types of
Too
Penrose
much.
diagrams, I think. Because anytime I bring up Penrose Pheely, I think you mentioned like these Penrose tiles or something. But when I think of Penrose diagrams, I think of like black holes and relativity. Because in this, I'm in a class right now, QFT and curved spacetime, and yeah, we're like, I finally learned how to like see a Penrose diagram or create a Penrose diagram, but not the tiled ones that you might think about, but like the ones that represent the universe and black holes. And from these Penrose diagrams, you get like the prediction of like different universes and stuff and white holes, and it's like really weird, but kind of neat to learn about.
Oh, just another example of that. A really cool graph I saw. It was for like statistical comparisons, and so it's called a Taylor diagram. But it's meant to show like how accurate different models are or different approaches are to like the real world data. And I was like, oh, is that something invented by the Taylor? But no, it's someone else with the last name Taylor, and it was made in 1996. So it's just there are too many Taylors out there in the sciences. And also, just as a clarification for seismic waves, so P waves are primary waves, which are compressional waves that, so they're like longitudinal, so they kind of squish back and forth. So those are the pressure waves that usually travel the fastest and so get there primarily. Whereas the secondary waves or S waves are shear waves that are transverse, so they're, instead of moving essentially back and forth, they're moving up and down. And those tend to be the more destructive ones because well, they move up and down more so than just pressure. But it's really cool because I believe you can hear primary waves. So you can actually sometimes hear like a boom if an earthquake's coming. But yeah, I guess that those went on a couple tangents out from our initial discussion. But if we transfer into our main topic, which this is a bit more of an impromptu episode where we didn't have too much of a plan. Some of us are traveling, so we didn't figure we would be able to record, but we are more than happy to sit down and record in the time that we have. So what's new with everyone in terms of your research or what you've been doing in terms of science communication and science in general?
Well, I just came back literally last night from the APS March meeting, which is the American Physical Society March meeting, which most of the people who attend there are, I think, condensed matter and soft matter people. So I had listened to very good talks, great talks, and meet new people who do PhD, postdoc, or faculties, new faculty, old faculties, like all kind of people. I think there are like 10,000s of people there, and it was in Las Vegas, Nevada. It was quite entertaining. It was quite good, but it's a lot of metaphysics for a week, and I feel like I stayed for so long. I took a short course there on like computational physics. I can talk about that at later on, but right now I'm just still processing a lot of things, and there are things I'm catching up with school and my research. So I'm not right now. I'm
I'm really
too
upset
much.
I didn't go. I should have went, but I don't know. I didn't. In my opinion, I didn't have enough to talk about. It's one of these really big, serious meetings that, like, I don't know. I feel like, I mean, I know you can go and talk about whatever you want, but I feel like I wouldn't want to go unless I had some big result or something. Also, trip to Vegas. I've never been to Vegas, and I really want to go. How was it? What's Vegas like?
Well, what can I say? So Vegas is a place where it's gonna suck your soul and try to rip you off of your
Sounds
money.
about right.
Yeah. Well, it's like a magic place built out of middle of the desert, right? So it's like, why would people live there? So I feel like the point when you're there is like, well, to have a good time and spend money. But you go there as a broke graduate student, well, then that's another story. So I was trying to scrape by, like literally just try to survive. And it's not fun, like that part is like, well, I have to worry about money, I have to worry about a lot of things. It's just not fun. I can see myself, like, if we were to go there when I actually like have money and go enjoy myself or do stuff, might be a very good place. But at the point where I was there, try to, I was sent there in a way to work, right? And try to not spend money and take care of my future
Yeah.
is not, to me, it's not the greatest place to do that.
I guess even if you went for like 2 days instead of a whole week, it'd be a lot more fun because it's like you can spend the amount of money you spent over the 1 week, but in 2 days instead. So tomorrow, Pheely got back yesterday, and tomorrow I'm flying somewhere for a week. So lots of traveling.
Yeah, I'm still like haven't slept much like at all for the past 2-3 days, like from traveling and stuff. So my mind is still a little foggy. So that's why I don't want to talk about
Oh well,
physics.
you're at the wrong place. Sorry. That's funny. Yeah, tomorrow I'm flying to our old undergraduate university, St. Francis Xavier University. Yeehaw.
Which they just they were at the
I don't think they won.
what's it called basketball national championship today, and they lost in a double overtime
Yeah,
tragedy.
I saw that.
Darn.
That would suck. But I mean, it was pretty. I mean, I don't follow sports at all, but to even get that far is pretty nice. I think they lost to Carleton, which is an Ottawa University.
Yes.
Yeah, we went to Carleton for Canadian undergraduate physics conference 1 year. Pheely and I and some other people.
Yeah, that was fun.
That one was really fun. We almost okay. I won't get into it. We almost got lost and we almost wandered into Quebec somehow. We were young and innocent.
Oh, innocent wouldn't be a description, but young, yes.
Anyway, steering the conversation back, Liam, what about yourself?
Yeah,
any
so I'm going
updates?
to Saint FX. I basically emailed our old profs and I said, hey, you guys should invite me to come give a colloquium talk so that I can add to my resume that I've been an invited speaker somewhere. And they said, yeah, sure. So that worked out well for me. And the university will pay for my flight. And I live pretty close to it. So it's basically just like a paid visit back home to see my parents and to talk about my research, which is kind of nice. I'm still working on the talk right now. Our old undergraduate university, it's a predominantly undergraduate university, so there's not really many like master's or PhD students there. So normally when you give a talk, you're kind of aiming it towards the graduate students and the profs, but here I have to create it for the undergrad. So I'm going to assume they know first and like half of second year physics. I think that's a safe assumption for anyone who's going to be at that talk. But yeah, it's been interesting because the only talks I've ever given before have been like 15-20 minutes long or even shorter. So this one I have like 40 to 60 minutes, right? So it's my first long talk. So I'm being careful to not get too hung up on things. I'm trying to like introduce subjects that undergrads might not know about, even just like trivial things. Like I say trivial, but like I remember as an undergrad, sometimes you'd be at a talk and there'd just be like some random notation on the board, and I'd be like, what the heck's that? And it's because no one ever taught it to you as an undergrad. So I'm trying to be careful about what I say and what notations I use. And
Just if you happen to be an undergrad at St. FX in physics and you are attending this talk, feel free to listen to our very first episode, where Liam talked about his research, and you might be able to get some
I
good
advertise
questions
this
from
podcast
there.
too. Our old prof, which one of we mentioned it the last episode with Kat, Carl. He's the one, or Dr. Adams. He's the one who's organizing the talks for for the physics department this year. I think the profs, they swap it off every year or two or something like that. And I had to send him like an abstract and a title and kind of a short bio. And in my bio, I made sure to say, also in my spare time, I run a podcast with two other Saint FX physics graduates, hyperlink. So maybe it worked.
Well, what I noticed actually at the APS March meeting, because most people have their PhDs, like, a lot of faculty, postdocs, and, the name tag doesn't say doctor because it would be weird, right? Like, just we call our professor doctor by and their surname, but like at the APS we just use our first name because you never know because most people have the doctorate and it sounds so arrogant to say like doctor or something, but people use their first name as like a normal
Yeah, and
basis, I guess.
I mean, I don't know. I'm one of the people that I don't want to be called doctor when if I'm ever a professor. I just want to be like, hey, Liam. And the way when we went to our undergraduate university, I think all the profs there were the same. Like, I don't think I ever called a physics professor Doctor so and so. We all just called them by their first names, which was really nice. And I'm still like that today. Like at McMaster, most of the profs they tend to just go by their first names. They don't expect you to call them Doctor. Um, Also, I don't want to be made a fool. I don't want to like when you apply or not apply, but when you like book a flight, it's like what's your title? And if you put doctor and someone's dying on that airplane, they're gonna come to you and say, "Can you save this man?" And you can say, "I study quarks" or something dumb like that. People are gonna be upset with you. So you gotta control your ego. You can't be going around like when you get your doctorate. Yeah, I think you're allowed to like flaunt it around for a few weeks, but you got to calm down pretty quickly, I think.
Just suddenly go change all your credit cards, your
Yeah,
license,
I'm not
everything.
going to do that. I think it'll just be like a joke amongst my friends. They'll just call me Dr. Liam or something, and I'll just shake my head at them.
But you're giving this talk, which is excellent, and I guess is another form of science communication
Hmm.
apart from the podcast. In terms of actual research, have you made any progress since we last did our update? I think just about
I
3
don't
months
even
ago.
remember the update or what we talked about. I got published finally, but I probably mentioned that in one of the most recent episodes. So I got my first publication finally, the ripe old age of 25, which I feel like most of my friends got published long before then, but I'm pretty happy about this because like this publication, it's like my publication. I did like most of it. I mean, of course, like my supervisor and this other guy we're working with, from England, they obviously did a bunch of stuff, but like I was kind of the driving force making it happen, and I was like emailing them saying, "Hey, can you check this?" or like, "Hey, I checked this. What do you think?" So I'm the first author, and I'm pretty happy about it. So I got published finally. Wonderful, excellent. More to come. Studying. I mean, every time I try and aim my research more towards like real life stuff, and every time it just goes more in the direction of like black holes and freaking quantum field theory. And I mean, quantum field theory is super applicable to the real world, but not. I guess you need to be studying like condensed matter systems for that. And I'm kind of going more in the black hole, like quantum gravity direction. So I want to try and get into these metamaterials. Maybe I've been looking at them a little bit over the last 3 days, but yeah. So there's that. Um, Passed my comp exam.
I do just want to say
Thank
congratulations
you.
on passing your comp exam. So we talked about this in an earlier episode where PhD students um, have to take this candidacy exam or this comprehensive exam to essentially continue on in their degree. And Liam successfully passed. So feel free to give him a little round of
Woo.
applause wherever you are.
Yeah,
Maybe
I'll
not
do
if you're
that.
driving.
What else? There's not much of an update. I'm in this class now, being taught at Perimeter Institute again. So it's this fancy theoretical physics place in Waterloo, Ontario, and we shuttle there every Friday and spend the whole day there. It's on quantum field theory and curved space time, and I'm loving this class so far. It's it's all about like particle production and pair production and the stuff we talked about in a recent episode. Um, so I actually kind of know what's going on in the class, which is really great because most of these perimeter classes, at least the ones I've been to before, it's all so above my pay grade that I have no idea what's happening half the time. But this one, I think I'm like, I mean, I'm not the quantum field theory expert, but I'm like the local pair production expert, like, I guess, somehow. I learned about the dynamical Casimir effect. That's a fun thing. So the Casimir effect was something I brought up. Did we ever talk about it? I don't know.
I think we briefly talked about the Casimir effect. That might have even been last episode
Yeah.
or the episode before.
So the
But not
Casimir
in
effect
depth.
is essentially you have like two conducting mirrors right next to each other. Or sorry, not mirrors, two conducting metal plates. And they're separated by some distance. And even when there's no current going through the plates, so they're just like metal plates, they conduct electricity. But even when you're not putting any electricity, you actually get this force between them, which pulls them together a little bit. And it has to do with vacuum fluctuation. So essentially, by putting these mirrors near each other, what ends up happening is that this boundary somehow creates an energy shift in your vacuum energy, which we talked about in another episode. Turns out the vacuum's not empty. There's these quantum fields there. I don't want to repeat too much stuff. But anyway, Casimir effect is basically these due to vacuum fluctuations, you get a little shift in energy of them by these boundaries of these conducting plates, and they kind of pull each other a little bit. So the dynamical Casimir effect is if you have like a conducting plate, or like I don't know if it's a mirror or a conducting plate. I want to say it's a mirror, but that doesn't match the original.
It's a conducting
Okay, you can
plate,
just have
I
like one of
believe.
them, for example. You don't even need two. And if you just move this thing, you accelerate it or move it through space, particles will be produced from it that'll whiz off of it. And it's different than Unruh radiation, which I've mentioned before. But they're all related. But it's different. So that was something I thought was neat, because I don't know if we've ever experimentally verified it, but it is like in theory something that's a lot easier to verify than black hole Hawking radiation, that's for sure. Yeah, anyway, my update is that I'm just having a good time over here learning stuff.
Patrick,
Yeah.
you have any update?
Well, I am trying to get my first paper as first author published. I have a couple publications, but that's as part of a collaboration, so I don't really count them. And they're still in physics, so I definitely don't really
Damn.
count them. But I'm trying to do work relating structural diversity of forests to its tree species diversity. And just within the past couple weeks, I was able to get very promising results. We opened up essentially data sharing and data communication with the Smithsonian Tropical Institute, or it's named somewhere along there, but it's run by the Smithsonian, which is the big organization in the United States, and it's based out of Panama at a place called Barrow, Colorado Island. And they have some very lovely data in tropical dry forests that we are now able to use, again, provided the proper citations. But yeah, using that data, it increases our data set by quite a bit, and it's showing some pretty promising results. So I'm looking forward to publishing that paper, hopefully soon. But our lab is also kind of switching over to machine learning and different types of machine learning algorithms and their use. So I might be including a component of that, which means I need to learn a lot about machine learning in a very short amount of time. I have some background, but it's not very broad, especially in terms of implementation. So that's something to look forward to. And then also field work coming up. We'll be doing field work right at the end of the dry season in Costa Rica. So be doing 3 weeks in 40-degree heat and beating sun. So that's something to look forward to, and then working with the government for the rest of the summer. So lots of interesting research and hopefully some good results coming up. Just as another update, they launched a new type of sensor that's aboard the ISS that's able to take what we call hyperspectral images of the Earth. So that's essentially a high spectral resolution from 400 to 2,500 nanometers. And I think within that there's 260 some bands or individual recorded wavelengths that we're able to use to make like spectra of different pixels, which is very useful. That's another sensor that's up and monitoring constantly, so we can use that data for future projects, which I won't get into too much now.
I think one of my favorite things about I don't want to say like grad school, but I guess learning more over time, which you do, and then eventually in grad school, you start to get your own research ideas. And I think our old prof, Peter Marslin, I remember him saying something like this to me as an undergrad about how when you do undergrad research, you don't really know what's going on. I mean, maybe you have some idea, but the prof just kind of says, I have these projects, which ones sound interesting, and you choose it, and you have a goal, but it's kind of like you're following someone else's goal. But getting into grad school, I'm finding I'm coming up with all these ideas on my own, and it's like, oh, what about this or what about that kind of thing. And I think that's the most fun part about it for me, at least. So this recent publication I did, it wasn't my idea; it was my supervisor's, of course, and I started working with him on it. But I'm starting to get all my new own ideas. I have all these like publication ideas for the future, so it's exciting. That's what I like about it.
Well, you talk like we know what's going on in grad school, but I feel like I still have, well, maybe I know more what's going on, but relatively to like where the search for truth is, I don't really know what's going on. Like I'm just like we are in a very early career as a scientist, like as scientists in general. Like we don't know
Yeah.
jack, right? Like I feel like when even you're like in this business for like 10-20 years, you still feel like you don't know that much about it because scientific knowledge is so vast. There's so many fields that like PhD you're expert in one, but there are like infinitely many, right? Like it's like, well, it's in a way it's a very humbling perspective. That's like, yeah, you study these things for 4 years. You think you know stuff, but like you will meet people in your field, like really close to your field, that study something really similar to you, but have really in like a different, distinct
Yeah,
insights
that's
on
very
what you work
true.
on.
One thing about my specific field, though, that I find is quite different from many other people's research is that when I find other like PhD students or other researchers, they're so like hyper focused on one thing, but somehow my work and like my supervisor's work, it seems to combine like every branch of physics into a single topic. Like my acoustic black holes, it's like I need to know fluid mechanics, I need to know quantum mechanics, I need to know this ultra cold stuff, I need to know gravity, I need to know this branch of mathematics called catastrophe theory, I need to know asymptotic analysis. Um, there's like it's just like so many different things. I need to know statistical mechanics, I need to know quantum field theory. Somehow I am not like, I'm not like your normal PhD student where I'm really good at one thing. I just have approximate knowledge of many things. So I don't know. You're right in the sense that like, yeah, many I can talk to people and they know so much more than I do because we're new in this field. But I have like a base level knowledge of a lot of different things that I think a lot of PhD students, they're just experts in one. So I find that I'm getting lots of different ideas by connecting all these different fields together. Although then having to go down and learn more about them, that's the hard part, I guess, because I'm jack of all trades, master of none kind of guy.
I mean, I totally agree. After switching into my new program from physics, I find it a lot more interesting because there's a lot of different things involved. Like I study forests and trees, so I need to know a lot about the biology of trees and the chemistry of trees and how light interacts with the trees and radiative transfer models and different models for gas flux within these forests. And then things like statistical analysis and machine learning now is what we're transitioning into. So I think there are definitely people who are very much focused on one specific topic and they are the expert in that very fine, detailed topic. But I feel like as, I mean, the world advances, technologies advance, you kind of have to be a bit more interdisciplinary or at least have a broader knowledge about these things as a PhD student and as a professor. Because I think the world is changing for academics. And I mean, knowing, for example, a whole bunch of computer science from a physics standpoint is almost necessary at this point to do
Yeah, well,
analysis.
I guess that's true, right? Like I'm over here thinking, oh, I feel like I know a lot of different topics because my research involves a bunch of different things, not just one. But I think you could say that about like most people's research is that it involves a bunch of different topics. It's just maybe I'm not aware of these other topics. Like I mean, in theory, I'm supposed to know like computational stuff because I have to numerically solve things and make simulations, but I've never really done it and I'm not good at it. So that's an area I am actually, now that I've spent the last 1 to 2 years catching up on QFT, I think I'm going to spend the last 2 years of my PhD catching up on computational stuff. Got to broaden my horizons and keep my like what do they call that? Like, got to have good job prospects or whatever. Got to make sure that if I can't get into a physics job, I have to have at least programming there so someone will want to hire me.
Yeah. And now's, I guess it's a safer place to do that. Whereas if you're thrown out in the world as like, I don't know, an industry researcher or professor, it's a little bit harder to find the time between writing applications for grants or teaching or all of that. But now it's a perfect time to teach yourself all like the computational science. Like we were talking earlier about finite element analysis programs on the computer for modeling fluid flow, and that's some cool stuff. But people do PhDs on just those programs. But yeah, it's a much safer space now. So that sounds good, Liam.
I think we should wrap this up a little bit, right? So I think we have pretty good conversation, which kind of
Yeah.
all over the place, right? Wherever it goes, it's very has a strange flow of, maybe you could say, it's a vortex of conversation. But I think we had a good time. But I think Patrick can tell us, well, everyone, about how you could reach us, which actually has changed in the past week.
Yeah, so there have been some changes to our hosting site, which I'll mention in just a second. But if you're interested in talking to us, if you want to reach out to us, if you have questions, or if you want to be on the show, we are always looking for people to share their interests and their passion for their topics. Just our last episode had Catherine Boisvert, who was specializing in atomic force microscopy. She reached out to us and wanted to be on the show, and we are absolutely more than happy to have her. It was a good episode. We've had other guests beforehand, and we will have other guests in upcoming episodes. So if you would like to reach out to us, you can send us an email. We are hyperthesispodcast@gmail.com. We also have an Instagram account. You can find us at the Hyperthesis. We post updates about episodes coming up. We also post other communications, such as if we're taking a break, when we're coming back. There are some behind the scenes looks. And then Liam has been a lot better for posting memes. So that has been enjoyable. And I'm sure he will post many, many more to come. Yes, he is our resident meme artist.
Just convert my everyday experiences into meme art. Mostly, yeah.
And they truly are beautiful. So check out our Instagram at the Hyperthesis. We are also found on YouTube. We haven't uploaded there in a little while. We're just working on the processing pipeline in terms of getting those videos out more efficiently, because they are resource heavy. But you can check out, I believe we have all of season 1 on YouTube with some excellent graphics by Pheely. Again, you can just search Hyperthesis Podcast and it should pop up. You will see our lovely background. And if you are interested in listening to us or sharing us with your friends, we are on pretty much every podcasting service under the sun. We are on Apple Podcasts, Google Podcasts, Amazon Music, and a whole bunch of other ones. And we are actually now hosted, instead of being Anchor FM, it was changed by Spotify. So now we are based on Spotify Podcast. So if you search up Hyperthesis Podcast on Spotify, we are there. So wherever you are listening to us, feel free to share us, give us a like, a listen, a subscribe, and a review. We would love to hear feedback about what you think of the show, and we are more than happy to have more guests on our show. So if you're an expert in your field, or if you're just getting started out in your field but want to talk about it, reach out to us, and we would love to have you on the show.
Nice.
All right. Yeah, let's hear Liam's short story before we depart.
All right. There's no relevance to anything we talked about today, probably. One time we all went to an undergraduate physics conference called OPAC. At Acadia University in Nova Scotia. And I was giving my undergrad talk about accelerated electrons, relativistic electrons, and some like big name in the field of like relativity or something was there. I don't know who it was because I was an undergrad and didn't know anything. But I remember he asked, he's like, "Does your model take into account spin, or do you need to take into account spin?" And I remember I just kind of panicked and I was just like, "No, not at all." And I just, I like shot him down. He's like, "It should." And I'm like, no way. Because I was just panicking. I was like, oh God. And I remember our old Peter Poole, who was Kat and Pheely's undergrad supervisor, was just like in the back of the room, like roaring the whole time. And sometimes I think about that and I'm like, God, that was embarrassing. It was really funny. It was a good lesson as well. If you don't know something, just tell them you don't know. There's nothing wrong with it, right? Like when you do these research presentations, and I guess just in life, like lying about it or just making a panicked guess about it is not gonna pay off in the long run. And I went and talked to the guy afterwards and I said, like, "Hey, I'm sorry, I just panicked that you probably would need to take into account spin." And he's like, "Yeah, I know." So he was chill about it, but it was kind of funny. Anyway, sometimes I think about that.
All right, that is one confession per se.
Yes.
Thanks for that, Liam. And so this is, I guess, the end of the episode. So I will talk to you guys next week. Have a good day.
Bye, everyone.
See ya.